Hello and welcome. In this last part, we're going to look at taking the second derivative. So we've talked a lot about how to take the derivative of a function, and sometimes we will call that the first derivative because we've only taken the derivative once. But after you take the derivative, you have a function, and you can take another derivative by taking the derivative of the derivative, and that's what the second derivative is. So in terms of notation, we have f double prime, which means the second derivative, and the way you can write it using the ddx notation is like this. It's the derivative of the first derivative, so it's the derivative of f prime. Using Leibniz notation, it's a little bit funky looking, but you write it d squared y over dx squared, so that means the second derivative of y with respect to x. And again, all it means is take the derivative of the first derivative. Using just prime notation with y's, you can write y double prime, which just means y prime prime. All right, so to see how it works with example 11, make sure I got the right color here. We have this function y equals 2x to the fourth minus 5x squared plus 23x minus 10. And to find the second derivative, we first need to find the first derivative. So y prime, we'll call it. We could also call it dy dx if we wanted to. I'm going to go with the easier notation. So the first derivative, using the power rule, would say that the 4 would multiply in front, you'd subtract 1 from the exponent, and you would get 8x cubed. Can you tell me the derivative of the second term? If you said 10x, that's correct. And then the derivative of 23x would be 23. And the derivative of the last term, the constant, is going to be 0. Remember these last two, we had special rules for those. In fact, in order, the first rule we learned was of the derivative of a constant, which is 0. The second rule was the derivative of c times x, which is just going to be c. It's basically telling you the slope of that line. And then the other two are the power rule. That was the third kind of derivative that we looked at. All right, so there's the first derivative of the function. To get the second derivative, we just take another derivative. So what would the first term of the second derivative be? If you said 24x squared, then that's correct. And then the second term would be 10. So there's the second derivative of y. Now when we talked about grounding our understanding of the derivative, we talked about the position function, which we used s of t to represent, and the velocity function, which we used v of t to represent. And we said that the velocity function really is just the first derivative of the position function. Now if you take a second derivative of the position function, or in other words, you take the derivative of velocity, you get what in physics they call acceleration. This is probably something that you're familiar with. So the second derivative of the position function is acceleration. Acceleration, as it mentions there, just measures the rate of change of the velocity function. It's how the velocity function is changing over time. So that's a little side note, and we'll circle back around to that in a future packet. Now you could keep going on. You could take the third derivative, the fourth derivative, the fifth derivative, and so on. And the notation would look something like this: f prime, f double prime, f triple prime. Once you get to the fourth derivative, it starts to get annoying to have to write so many primes, and it's hard to count them. So what we do is we write f, and then like an exponent up there, we write a 4. But unlike an exponent, we're going to add these extra parentheses to kind of signify that we're talking about the fourth derivative there. Plus it's coming up as an exponent of a function name, which means it's not actually acting like an exponent. So the example here is f of x equals 4x cubed minus 2x squared plus 5x minus 1. Take the first derivative and you get 12x squared minus 4x plus 5. The second derivative and you get 24x minus 4. And then the third derivative, you get 24. The fourth derivative becomes 0 because, again, the derivative of that constant is 0. And then the fifth derivative is going to be 0. And as you can probably guess, the sixth and the seventh and the eighth and the ninth and the 10th derivatives will also be 0. This always happens with polynomials. They always eventually go to 0 if you keep taking derivatives of them. All right, and if you keep taking derivatives of the exponential e to the x, as another example, it just stays e to the x. So the 100th derivative of e to the x is just e to the x. Now the last thing I wanted to cover here is example 12, which is going to seem at least a little bit tricky at first, but we're going to take it step by step. Here we have y equals x times sine x times cosine x. And it's a little bit tricky because with the product rule, we only had 2 functions that were multiplied together. So how do we handle it when there are 3 functions multiplied together? Well, you can take it step by step. So what I'm going to do is I'm going to take x sine x to be f and cosine x to be g. So I'm grouping together the x and the sine x as the function f. That way I can still use the product rule. I mean, after all, x sine x is a function, so I'm just going to call that f, and then the other part, cosine x, is a function, so I'll call that g. So now with the product rule, I'm going to write dy dx equals first times derivative of second plus derivative of first times second. So here's the first, x sine x, times the derivative of the second, which I'll procrastinate and do later. The only time procrastination is good is when you're first learning how to do this. And then plus the derivative of the first times the second. So derivative of x sine x times cosine x. Now let's go ahead and see how to take these derivatives. They're definitely derivatives of smaller functions. And we can take the derivative of cosine x. What would that be? If you said negative sine x, then that's correct. Remember that the derivative of the c trig functions are negative, and sine and cosine just go back and forth between each other. Now, how to take the derivative of x sine x? What do you think you would do in that case? If you said use the product rule again, that's correct. After all, this is the derivative of the product of 2 functions, x and sine x. So we're going to go ahead and use this product rule to finish the problem off. So here I'm going to open up some brackets just to be safe. The product rule explodes into 2 terms, and so we're going to use those brackets to capture that explosion into the 2 terms. So we have first times derivative of second, so x times derivative of sine x, plus the derivative of the first, derivative of x, times the second, so times sine x. All of that times cosine x. Now we have even smaller derivatives to take. So here we have derivative of sine x, which is cosine x, and then the derivative of x, what would that be? If you said 1, then that it would be correct. While we're at it, we'll go ahead and simplify. So this will be negative x sine squared x. We'll put a plus, and then I'm going to reduce these. I'll keep the brackets. So we have x times cosine x. It's supposed to be a times there. And then plus 1 times sine x. Yeah, close bracket. And then just clean this up by taking the cosine x and distributing it to each of these 2 terms. So we have plus x cosine squared x, and then plus sine x cosine x. And that would be pretty good for simplifying that. There's probably more you could do. You could combine these 2 into a x times cosine 2x using a trig identity, but we're not going to go there. All right, so that is the end of packet 5. Thank you for watching, and see you in the next video.